Alright, welcome back to our online discussion of math. Today we are talking about permutations in our Scribblecast. We're going to look at evaluating factorials and using permutation formulas, and then using those to solve some related problems. To begin with, just an idea of what permutations are. When I was a youngster, my phone number was 78750. And all you had to do in Lethbridge was call 78750 and you got me. But then quickly we got other numbers, like I remember when 328s came out. And so instead of a 7 there would be an 8. And so then because of that and because of the 381 numbers that came in from the west side of Lethbridge, we had to change our phone number. So now instead of just dialing 78750, I had to dial 3278750. Oh, was that ever a pain in my neck. I remember my buddy's phone number was 70302. I still remember that one. And but then we had to add this 32 there. And then we had to memorize these other prefixes, which was sort of a pain. Now, and this will date the video a bit, but now they're making us to dial a local number. Instead of dialing 7 numbers, we're going to have to dial 10. So we have to add the area code in front of there. And they're making it so that you can't tell where a person's from anymore, because it used to be 403 was Alberta. Then we got a 780 up north there, but now they're giving us another area code, and apparently now it's a free-for-all. So you could, if you got a cell phone number, you could get it from anywhere. At any rate, we're going to have to dial 10 digits. So start learning how to put numbers into your phone so you can store them and not have to dial all of them. My purpose for bringing this out is that phone numbers are an example of permutations. They are arrangements or orders of numbers in which order is important. For example, 78750, if I had mixed that order up and got 78705, then, that's a 7 in there, although it has the same numbers in it, it would have gone to a different place. Because phone numbers are examples of permutations where order is important. So a permutation is arrangement of objects or symbols into distinguishable sequences. Each unique ordering is called, it's a permutation, and in permutations, order is important. Whoops. Order is important. So if I said how many 2-letter permutations are there using the letters from the word math, where you can't do repeats, well, I'd look in here and say, well, I guess I could put an M there and then an A there, and that would be one permutation. And if I didn't do an MA, if I did say an A then an M, that would be a different permutation. Now, one of the problems we get into is that, yeah, this might be an easy one, that I might be able to put all the ones in that I know, and there might be 12 different ones. But it might be hard to determine exactly how many permutations there are. So what I can do is I can use something called the fundamental counting principle. And we'll see this on a slide that comes up later. But what that does is it says if you have 2 things to fill or 2 events to happen, just figure out how many possible ways there are for this one and multiply it by how many possible things there are for this one. So in this case, I have 4 letters from which to choose to put in the first slot. If I can't use a letter twice, then there will only be 3 letters to use for the next one. So 4 times 3, there would be 12 permutations of 2-letter arrangements using the letters from MATH. Phone numbers. Let's see how many phone numbers I could get. I live in Tabor. 223 is our phone number for most of the people that live in Tabor. We'll see how many people there, or how many phone numbers there'd have to be in Tabor and surrounding area before we'd have to go to another number there. Well, in here, I could probably put in any number from 0 to 9, so there'd be 10 options. In this one, there'd be another 10, because I could repeat. And this one, another 10 and another 10, because I could repeat each of those. So with a 223 designation, 10 times 10 is 100, 1,000, 10,000. So there would be 10,000 permutation or 10,000 distinct phone numbers if I just have 223 dash something. And indeed, any time you have 4-letter permutations, you'd have of numbers, you'd have 10,000 different options. You might have to subtract a couple for police or for some other number that you can't use, but for the most part, there'd be close to 10,000 different permutations or different phone numbers that I could get using this prefix. Now, Tabor's getting bigger. We've got like 6,000, maybe 7,000 people here. I can see the day where, heaven forbid, they might make us use another prefix out front there instead of 223. I guess we're having to use the 403 or area codes all the time now anyway, so okay, just a little bit hard on me. Another way that I could look at permutations is using tree diagrams. So here I'm asking how many arrangements are there for letters A, B, and C. So I could go A, B, C, or maybe I could go A, C, B, or I could go, okay, I'm getting confused. And you can see how you might not be able to remember exactly where you were. You've got to use some kind of pattern. Tree diagrams are helpful for that. So you can say, okay, I could start with an A, then I could do a B, or I could do a C. If I did a B, then my last one would be a C. But if I did a C, my last one, of course, would have to be a B. And those are all the different permutations that would start with the letter A. Let's do the ones that start with the letter B over here. So if I start with a B, then I could have an A, or I could have a C. If I went with an A, my last one, of course, is a C. If I went with a C, my last one, of course, would be an A. So here, there were 2 permutations. Now I've got another 2, and of course, with the last one, I'm going to have another 2. So up here, I could say there would be 6 permutations or arrangements using the letters A, B, and C, where you can only use them once. Now, in just thinking about that, I could also use the fundamental counting principle, because I have 3 letters, right? How many could go in this one? I could go 3. How many could go in the next one? 2, if I've already used one. And in the last one, I could only have 1. So fundamental counting principle says how many for the first thing, for the second thing, for the third thing, times them together, you get 6. Using our tree diagram, we got the same thing. So this fundamental counting principle, this is what it states. To determine the total number of ways a combined action can take place, combined action, so the 3 letters being put together, I can use the fundamental counting principle. Or determine the number of ways for each separate event and multiply. And that's what the fundamental counting principle says. So for example, here's another one. Jessica, Tanner, Caitlin, Jeff, and Donna are candidates for president and vice president of the swim club. In how many ways could this happen? Well, I want to pick a president and I want to pick a vice president. Fundamental counting principle. Can you see it? So now I just say, okay, how many people could I have in for president? So 1, 2, 3, there's 5. Now, if I already pick one president, I can't have him for VP too. Although in baseball they do have managers and general managers that fill the same role. But in this one, no. One president, one VP. Can't be the same person. So if I've already picked a person for the president, I won't have him to pick for vice president. So there'd be only 4 options, having already picked a president. So, with 5 people, there would be 20 different permutations of picking a president and a vice president. Here's another question. I have a new software company, plan to sell at least 50,000 licenses for software. What kind of product key would I have to use so that all licenses were distinct? Okay, well, usually license keys have letters or numbers in them. Let's just see how many. So say I had, say 3. Say I had 3 numbers. So I'm going to put a number here, a number there, a number there. So this event, there could be 10 numbers. I could reuse a number, so I can put 10 there, and I can put 10 there. So if I only used a 3-digit product key, oh, that's not going to be enough. That's only 1,000 different licenses, I need 50,000. Well, okay, I could put another number. So let's go with that again. So instead of just 3 numbers, maybe I could go 4. That'll only give me 10,000. Now I'll be cool. I'll give them another one. So that'll be 100,000. 100,000 licenses. I want to have at least 50,000. 100,000, that should cover it. All I'd have to do is just have a 5-digit product key, and I would have at least 100,000, or I would have 100,000 different license keys for that. Yeah, you know, but that's okay, but maybe my product is really cool and it's going to sell to everybody, like a Cabbage Patch doll. Okay, again, that dates me. So I could put another number, or why don't I get adventurous and throw a letter in there somewhere? So let's put a 10, and so a number there, and then let's put a letter. 26 letters times maybe another number. Let's throw in another letter. And maybe for good measure, let's throw another letter at the end. Multiply those together. I don't have my calculator with me, but that'll tell you how many different license keys there would be. And with that, there would be ample. Nowadays with Microsoft, boy, they've got a ton. Like to type in their product key when you buy something from them, you've got, I don't know, 20 digits long. Just think about how many distinct product keys there would be with 20 digits. Boy, that'd be a lot. All right. Now, with sometimes where, like that vice president thing, where you pick some and then you can't use one of those for the next pick, we can use something called a factorial notation. And we use that just as a simple way to indicate that there's so many different ways of doing something. So say, for example, if I have 10 people and I want to arrange them in a line. So how many different ways could I arrange them in a line? Well, the first person, there could be 10. The second person, since I've already used a person, I could have 9. And you can see how that's going to go down the row. Whoops, that would be a 7 times 6 times, etc. Well, rather than writing all of those out, what we do is we say, well, that's 10 factorial. And this symbol in math, exclamation mark in math, reads factorial. You can find it on your scientific calculator. If you have a graphing calculator, usually if you hit math, it'll be in one of those little menus down there, factorial button. Anyway, you just type 10, hit the factorial button, and it'll pop out the number of different arrangements that you could get. But factorial is used when you have that, you use one and you can't use it for the next one. Like you couldn't use this factorial for this one because I had 10 numbers that I could use here, but then I could reuse, and so I'd have another 10 here. I couldn't use factorial here because factorial says start with 10, once you've used 1, then you've only got 9. Once you've used 2, then you've only got 8, etc. Here's something you can do on your calculator if you want. Figure out what 4 factorial it is. I could write it out. 4 times 3 times 2 times 1 be 24. Try it on your calculator. Here's an interesting one. You can do some games with factorial where you have 9 times 8 times 7 times 6 times 5 times 4. I need to keep going there. But on the bottom I have 3 factorial. Here I'm going to have times 3 and I have to keep going. But rather than keep going, I can just write 3 factorial. Then these two would cancel, and all I'd have to do is figure out what that is. It's probably easier just to do it on your calculator where you go 9 factorial, divide 3 factorial, bam, out pops your answer. Similar thing that you can do there. To determine factorial, you can also use or not to determine factorial, but to determine the number of permutations that you have for an event. You can also use a formula. There's a button on your calculator, but there's also a formula, this one right here, that you can use to determine the number of permutations you have for an event. So say I've got 10 people and I want to make a presidency of 3 people. So a president, a vice president, and we also always need a treasurer. So 3 people. So I have 10 people, and from those I want to know how many different arrangements I can get a president, vice president, and a treasurer out of that. So what I can do is I can use this permutation formula. And N stands for the total number of objects, in this case people. R stands for the total number of people or objects that you are drawing at a time. So in my example, if I have 10 people and I want to fill 3 slots, so I have 10 people and I want to find how many permutations I can get when I'm picking from 10 of 3 people at a time. So on my calculator, I can just go 10, pick 3. Or up here, I could use this formula here, which would say 10 factorial over 10 minus 3, or 7 factorial, and I could figure that out. I might as well just do it here. 10 times 9 times 8 times 7 factorial, 7 factorial on the bottom. So I just have to go 8 times 9 times 10, 720. So there would be, from 10 people, 720 ways I could choose, or not choose, I could pick 3 of them. Okay, so that's a permutation formula. Try these ones on your calculator, or try them using the formula. I won't write the numbers down here, but you can determine those. Okay, here's another example, and again, similar to one we've just done. How many 3-letter permutations can be made from the following word? So I have the word Hamilton. Notice that none of these repeat. If they repeat, special things I have to worry about. But here I've got, looks like I've got 8 letters altogether, and I want to know how many permutations I can make, and just using 3 letters. So I need to go 8, pick 3, and figure out what that would be. So 8 times 7, 56 times 6, I don't know what that is, 336 or something. I'll write it in there, but I'm not sure what it multiplies out to. But it's 8, pick 3. Here's another example. Hey, we did this one before. 5 people, from them I'm picking 2. And we did that before, but we used the fundamental counting principle. But here I can say, hey, I've got 5 people. Order's important, because one's a president, one's a vice, so I can pick 2 of them. So 5, pick 2. I think that, before I think that came out to 20. Now sometimes, if you have non-distinguishable objects, people, this won't work. I guess twins, you might call them non-distinguishable. I don't know. There's typically with twins a way that you can tell them apart. But if I have, say, balls, 5 red balls and 10 green balls, and the balls are indistinguishable, then that has a bearing on how many permutations I can get. Like, it lessens the number of permutations by quite a bit. But here's a formula I could use to determine that. And basically what they say is, you take whatever n factorial is, and then you divide it by how many things are repeating. For example, how many 3-letter permutations are possible using the letters from the name Bob? Okay, so there's Bob. There's 3 letters altogether. So how many 3-letter permutations? I could write 3, pick 3 if I wanted to. But then I have to divide it by anything that's repeating. B is repeating twice. So since there's 2 of the same letters, I divide this by 2 factorial. Now, 3, pick 3, I guess I could have done it this way. I could have said 1 letter, 2 letters, 3 letters. And initially there's 3 to pick from, and then there'd only be 2, and then there'd be 1. So there'd be 6 ways that I could rearrange Bob. But because there's 2 B's that are the same, I have to divide that by 2 factorial, which is 2 times 1, or just 2. So there'd be 3 total permutations of 3-letter orders using Bob. Okay, you're probably dying to get to Mississippi. Pause and see if you can figure out how many arrangements of the word Mississippi there'd be. Okay, hopefully you pause there. Here'd be the answer. Count up how many letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there'd be 11 factorial ways of rearranging those letters Notice I'm not picking some from there. I'm just rearranging all of them, like I did with Bob. 11 factorial. Now I have to divide that by the repeaters. M, there's only one. Okay, now i's. 1, 2, 3. There's 4 i's. So I'd have to divide this by 4 factorial. Oh, and there's 4 s's. So I have to divide it by another 4 factorial for the s's. Is that it? Oh no, there's 2 p's. So divided by another 2 factorial for the p's. So that would give me the total number of arrangements using all of those letters of the word Mississippi. Okay, so today we have looked at permutations, found that they are orders of or arrangements of letters or numbers or whatever we have. The key thing was that order was important. Try some questions in your text and on the quizzes. See if you can use those formulas, the formulas and the concepts we talked about in this section. Thanks. We'll see you later.